Righto, this thing is a filament runout and filament jam detector, but it's also an Extruder black box flight recorder. This thing is nuts. It shows moment by moment what the extruder is doing in real time so that if there's a problem, it can often be fixed before the print fails. I love this thing. Quite a while back now, I'd put up a video about a filament runout and jam detector that I'd come up with that worked by using some electronics to detect when the movement of the filament did not match the number of extruder motor steps coming from the 3D printer motherboard, and would pause the printer so that the problem could be sorted. And this was more functionality than a simple runout detector. But often when the printer paused, it was difficult to tell what the problem was that had actually stopped it. And also it was kind of fiddly to set the sensitivity accurately. I think this new design is another jump forward. I've been using it on my trusty TiVo Tarantula for some months now, and I've found it really useful. Now I've redesigned the filament detector box so that it is easier to see what the wheel is doing and to get to the LED and the photo transistor for adjustment. It's also less bulky and lighter, so I think it could be easily adapted to use on a direct drive extruder, although I've never actually tried to do this. My only printer is a TiVo Tarantula and has a Bowden setup. So how does it work? Well, like the original version, the filament movement detection is done with a slotted wheel and some optoelectronics. Infrared light is produced by an infrared light emitting diode, and this shines through the slots in the slotted wheel to the infrared phototransistor on the opposite side. And the light is interrupted by the spokes between the slots as the wheel turns. And this causes the voltage output from the phototransistor to rise and fall in a sort of sinusoidal fashion. Okay, so to give a bit of an idea of what the wave looks like, I've hooked this up to a Bitscope digital oscilloscope, and you can see the tracing on the screen. It's more or less a sine wave. Okay, so the rest of the electronics is in a separate display box, which is this part here, that could be mounted somewhere on the 3D printer in a convenient position. It's connected to the filament movement detector box by 3 wires. There's just the positive and the negative, which are just power supply wires, 5 volts, and the yellow wire in the middle is the voltage signal from the filament movement detector, the phototransistor in there. So I've just clipped this onto the front of the plastic of the motherboard housing. Let's have a look inside. So I'll just pop this open. Oops, there we go. It's all just clips together. So if we can take that out of there, there we are. Okay, so this is the board. So let's take it apart. This is the first component you come to, is the display. So this is a OLED display. It's 128 pixels across by 64 pixels deep, and it's got 4 pins to connect to the microprocessor. So 2 of those pins are actually power supply, 5 volts plus and minus, and there's also 2 other pins for the data. And this module uses the I2C bus, which then can just connect with 2 wires quite simply to the I2C output on the microprocessor. And it's 1.3 inches across, and they're quite cheap. I got this one from Banggood. So let's have a look at the rest of the board. So the main component that you can see there is the microprocessor. This is an ATmega 328. It's the same processor that is used on the Arduino Uno, and that is how I programmed it. So here's a Arduino Uno. Let's get that in focus. So these are a board that's got all the pins broken out to various sockets and things, so they're easy to interface to breadboards and things, and they're great for developing microprocessor programs and things and hooking them up to gadgets and what have you. The board has a USB connection that can just plug straight into the USB on a computer or laptop, and it can also power it as well. There's a separate power socket for powering it if you need to, but so that's the same chip as we've used. It's an ATmega 328, and I programmed it on the Arduino Uno, and to program it we use the same software, in fact, that is used for programming the firmware on the main board of the computer. And a lot of people will be familiar with the Arduino IDE, or Integrated Development Environment. So that's the Arduino that we use to program it. So getting back to the circuit board again, there's a few other components on there. There's some push buttons which are for sending commands and selecting things on menus. There's a beeper, which is that round component there that's powered by a transistor. It's used as a switch basically to switch the beeper on and off, and that hooks up to one of the data pins on the microprocessor. There's the crystal and a couple of ceramic capacitors, which basically just provides the crystal for the oscillator on the microprocessor, so it provides a 16 megahertz clock signal to drive the microprocessor. There's a few resistors. I think there's about 3 resistors in all. This button here is the on-off switch, and there's a couple of capacitors for smoothing out the power supply. But it's a lot simpler than the board that I used for my original filament detector design, so it's a bit simpler than that. And it's all just made on perf board, and I just make solder tracks rather than trying to print out a PCB. I find for small projects it's often a lot quicker just doing it that way. Okay, so the microprocessor has 2 wires that connect to the 3D printer main board, as well as 2 other wires that are the power supply. So there's a positive and negative 5 volt wire as well. So I'll just show you how I've connected this. Now, most 3D printer main boards have microprocessor, obviously, and this processor has various pins on it that connect to the stepper drivers. So one of the signals we want is the step signal that goes from the microprocessor to the stepper driver for the extruder. Now you could perhaps solder or work out which pin it was and then solder a wire onto the board, where that connection is. It would be very difficult. You'd have to solder it onto one of these very fine pins, which are surface mount components. It's very hard to solder onto a accurately onto one of those pins without short circuiting things and what have you. So it's better to use one of the pins that is actually broken out on the board to a solid physical pin that you can just plug something onto. And the pins that I use for this are spare limit switch sockets, the pins in those. So this the pin actually for the stepper motor that I used, stepper driver, was this pin here on the X plus limit switch. So I've reconfigured that pin in the Marlin firmware so that it's actually a copy of the step signal that is sent to the extruder stepper driver. So there's a plug with 3 wires that goes into there. So on that socket there's also a positive and negative power connection as well, so they're handy. So that's where it gets the filament detector board gets its power from. is from those two pins, and the step signal comes from this one. And then it needs an extra pin that is used as the connection where the detector can signal the motherboard that there's been an error and the board needs to, the print needs to pause. And so I've configured another pin. This was the Z plus pin for the Z plus limit switch. I've reconfigured that so it's now the pin for detecting filament runouts and things and pausing the printer. But it does mean modifying the firmware, and where I've posted this project on Thingiverse, there's detailed instructions about how to modify the firmware so that those pins can be used in that way with this device. So let's have a look at the filament detector in operation. So we turned it on with the on-off button and the extruder detector splash screen appears, and then we are presented with a graph that slowly walks onto the screen from the right hand side. So what is the graph actually a graph of? Well, the filament motion sensor detects motion every time the filament moves about 0.5 millimeter. So what the device is doing is it's counting how many steps the extruder motor takes for each 0.5 millimeter of movement of the filament, and it then plots this number on the graph each time motion is detected. You'll notice that the number of steps is also shown in the lower left hand corner of the display, and sometimes that number is replaced by some arrows, so when there's a retraction motion the filament detector doesn't try to detect errors in that time, so that number is replaced by a double-ended vertical arrow. And the way the filament detector works out that retractions occurring is because the time interval between the step signals is a lot less, just because the retraction motion is a lot faster. So it can tell how fast the filament's going. If it's going fast, it assumes that it's a retraction and doesn't try to graph that. Once the retraction motion is finished, the device waits for the next detection of the motion, so it knows what position the wheel's in before it starts counting again, so we don't get errors from it not knowing quite where it lands after a retraction motion. And while it's waiting for that, there's an arrow shown again that just points to the right. The other things that are shown on the screen, there's a little pause symbol. So when that pause symbol is shown, it means that the device is enabled to actually pause the 3D printer if an error occurs. So there might be situations where you don't want it to be stopping the printer all the time, in which case you can disable the pause function in the settings, in which case that icon will have a little diagonal strike through it. There's also a little bell symbol, so that symbol indicates whether or not the beeper is enabled. So if that's enabled, what will happen is that whenever the count goes out of range, there will be a beep from the device. And there's also a number next to the bell, which is the number of errors that have occurred in succession. So it's possible in the settings to actually set the device so that it takes more than one error to cause it to pause. So you might set it so that you have to have 4 errors in a row to pause the device. And so what that number next to the bell there indicates is the maximum number of errors in a row that have occurred. So if there's been 2 in a row, then it'll show a 2, and it'll stay showing a 2 until 3 occur, and then it'll in a row, and then it'll be updated to 3. So it shows the maximum number of errors that have occurred. So that can be quite useful for setting up these settings that control the sensitivity of the device. You'll notice also that there's 2 dotted horizontal lines, one at the 30 position and one at the 55 position. These are the thresholds that the device allows before it'll say that something's an error. So if the count goes above 55 or under 30, then it'll say that an error has occurred. And those thresholds can be set in the settings menu as well. Okay, let's have a look at some examples. So this first one is a situation where the printer is under extruding, and most commonly this is due to blockages in the nozzle, or the nozzle's too cold for the type of filament being printed, or perhaps if it's a filament that requires a high temperature, maybe we're trying to print too fast with it and it's not allowing enough time for the filament to melt properly as it goes through the extruder. In this situation, the number of steps required to push the filament through the same distance increases, and so it tends to go above the upper threshold and then it'll beep. And I've got a view here of the extruder gear itself, and it shows that the extruder gear is turning, but when the error occurs you can see that the idler wheel stops, and so there must be slippage between the filament and the extruder gear, and so it's not extruding properly at that point. I think being able to detect under extrusion like this is actually really cool, because you can see small degrees of under extrusion occurring on the graph long before you'll start to see anything happening with the model itself. I mean, really, to be able to actually look at a model and see that there's been under extrusion, there has to be enough of it to actually be visible, and so by that time basically the model's ruined. Whereas with this, you see small degrees of under extrusion, or you get alerted to run of under extrusion, and you can often fix the problem and save the print. Okay, this next example is where the stepper motor is skipping. So often this happens when the motor's under a lot of load, and it can be due to a number of things. It can be due again to problems with the nozzle being clogged, or the temperature being set too low, or trying to print too fast. It can also be due to the voltage setting on the extruder driver not being set correctly, but if it occurs as a new problem, it's probably more likely to be due to some sort of obstruction. In this case, it was actually due to me having replaced the spring on the extruder. The old spring had weakened and was allowing the gear to slip, and that was causing under extrusion, and so I'd actually stretched the spring, but I think I'd stretched it a bit too far, and it was sort of crushing down on the filament, but it also increased the drag on the extruder motor and led to this problem. You can actually hear a slight audible click from the motor when it occurs as well, but this is an example of what this looks like on the filament detector. So finally, let's have a look at the menus. And as a demonstration, I'll start off with the calibration of the optical movement sensor being out of whack. So if this happens, we get this big thick tracing because the microprocessor is not using the correct thresholds to detect when a spoke or a slot moves in front of the phototransistor. So as a slot moves across in front of the phototransistor, the number of steps that it takes should be the same roughly as the number of steps it takes for a spoke to move across in front of the phototransistor. And if these are different, if the thresholds are set so it records more steps to move a slot across, say, than a spoke, then what will happen is that as the wheel turns, the graph will just spike up and down alternately as a spoke and a slot go across in front. So we want the number of steps for a slot to move across to be about the same as the number of steps for a spoke, and that's calibrated in the last screen of the menu. So we access the menu by pushing the OK button, and the first screen we come to is the screen for toggling the state of the beeper enable, so it can be toggled on and off with the up and down buttons. The next screen does a similar thing for whether or not the filament detector will pause the printer if there's an error, and we can toggle that up and down with the up and down buttons. And then we can go to the next screen, which is used to set the max threshold, so that's the height of that top line on the graph. And so if the graph goes above that threshold, then it records it as a error. And likewise we can set the minimum threshold, and we can set the number of errors that will be tolerated before the device pauses the printer, or just stops recording and freezes the graph if the pause enable isn't set. And then we come to the retraction threshold. So now this value is used by the microprocessor to determine whether or not the extruder is retracting. So generally the filament moves much faster during retraction movements, and so the speed of the filament can be determined simply by timing the interval between the extruder step signals. And the shorter this interval is, then the faster the extruder motor must be turning. So if you ever find that the filament detector is detecting extrusion when it's not actually happening, then you can just reduce the threshold value here, and vice versa. If the filament detector is not detecting retraction movements, then you make this value longer. And you can get some idea of what the actual interval is between steps by watching the value of the last that's listed there. That's the last interval that was recorded, and it updates as the speed changes. And this gives you some idea of what the interval is for normal printing speed and for retraction. So you can work out from that where to set the threshold, which should be somewhere in between the two. And next we come to the screen for calibrating the optical filament sensor thresholds. So this is a busy screen with a number of values displayed. So the microprocessor converts the signal from the infrared phototransistor into a numerical value by using a 10-bit analog to digital converter. So the value can range from 0 to 1023 in theory. So the top line shows the actual range that's being received by the microprocessor. So it'll want to set the threshold somewhere in between these values. The next line there shows the thresholds that are going to be used if the setting's saved. So the up value is the value used to detect the transition when the sensor goes from dark to light, and the down value is the threshold where it will sense going from light back down to dark again. The steps up value is the number of steps that the extruder took while it was in the sensor was detecting that it was in the light, so it was in between the up threshold and down threshold. And the down value is the number of steps that the extruder was taking while the sensor was registering that it was in the dark. So basically the up value is the number of steps per slot, and the down value is the number of steps per spoke. And we want these values to end up about the same. So there's the same number of steps per spoke as the number of steps per slot. And if they're different, the microprocessor adjusts the thresholds by the amount shown as V-adjust or V-adj to bring them closer together. So after the calibration's been running for a while, you'll find that the V-adj value will settle into varying over some range. It'll sort of oscillate up and down. And if you make a note of what the top value and the bottom value is, and then just hit the down button to save the calibration when that V-adjust value is somewhere in the middle of that range that it's sort of oscillating over, and that'll calibrate the thresholds for the optical sensor. And here we see the results. So in the tracing now, it's much narrower than it was before. I mean, it'll always vary a little bit because we 3D printed the disc, and there's probably going to be some slight variation in the width of the slots and the spokes. And also just the variation as the filament goes through the extruder. It's never going to go through at exactly the same rate. But if you get into a narrow band like that, then that's quite adequate for what we're looking for. Okay, so there it is. I've uploaded all the STL files needed for making the various plastic parts to Thingiverse, as well as detailed instructions for making the electronics and programming the microprocessor, as well as the program for the microprocessor itself. Plus I'll also upload the CAD design as some step files so that anyone can change the design around to suit their own setup. And I'll put the Thingiverse link in the description. So hit me up in the comments if you have any questions, and happy printing.